Can you just look up casing purple?
Yep.
There it is.
Casing purple.
Did you like name it earlier?
Yep.
Define casing purple earlier.
Casing purple is a defined color.
Or did you ask for permission to use that?
No, because he did it. I learned from my professor.
It's just a color.
You could ask for permission. You can use it.
Well,
No.
We're still kind of butthurt. School got mad at us.
They got mad at us for using their color on like our ANS polos.
Yeah, the
We're use a slightly different. I also need to use like a slightly different color. Yeah.
Who?
Because they own the copyright of the color.
But
Like the direct X code color.
what?
No, they got
Not X code, remember the color.
and the power cat.
I can read it to you.
The power cat.
So I know that logoing is definitely something they're weird about.
No, they started cracking down on that like what, 2 years ago?
Yeah, but to have limits on the use of a color seems like I would go out of my way to tweak them and use I would paint myself that color and walk into their office. Yeah, I can't stand that sort of
At
thing.
least they don't have.
You know, Roberts, I would love it if you did that.
How can
512-888.
That's serious.
is that the Pantone color?
I guess.
Yeah.
That's what I have my variable set as. I'm sure that.
Or is it the hex code?
I don't know the format of a hex code.
Hex code is always a hash symbol with 6 numbers.
Yes.
Yeah. All right. So let's
They're all struck with studying for detection. They have the detection power for this.
Is that why everybody wanted me to just talk about differential equations in review today so that it could be skipped? Yeah.
Wow, that's thinking ahead. Dang.
So,
I need a differential equations.
Yeah.
All right, well-
Roberts, we're here because we wanted to be.
all right. So I have started putting together some notes for this, similar to what I had done for the eigenvalue material. So I'm going to kind of walk through notes as in this format because I didn't have time to put it into something like a slide. I also do have my tablet. I think I got my pencil working so that it's not going to drift or whatever. I do have a lot of revision to do left on this, but I thought I would just dive in and kind of show you what I'm hoping for. Again, you as an audience are different from what I might expect teaching this, starting next year, because you've all, or many of you have reactor theory already, and that you'll. Those who have had reactor theory already will look at this material from a different way than somebody who hasn't had. I'm hoping that it just becomes an accessible starting point for understanding mathematical modeling of phenomena that includes neutron diffusion, heat transfer, and other things that we care about in engineering domains. Okay, so what we're going to use today as a starting point, or as let's say a flexible representative model, is called the Advection-Diffusion-Reaction Equation. If you've had reactor theory, you've heard of the diffusion equation, and that specific diffusion equation would actually be a reaction diffusion equation. Why? Well, because you have neutrons interacting with something. Right? If you have a cross-section term, you have a reaction. Diffusion, of course, relates to spatial motion of some species from a local domain. Okay, the one thing that we haven't covered before in say reactor theory is advection, but my guess is you're familiar with the concept of advection from a class like fluids, where you have a mass of material, control volume of material, possibly that is flowing at some speed. Right? At least in principle, you've heard that word before. So advection is one word, convection, related word. I'm not sure. So if you think about the Greek, ad means to, I think, and con means with. And I think the vect would, in this case, be a direction. So taken along with a direction or a convection, or going along a direction, advection, both of them carry something away. Just make sure that we have. Have you heard advection? Is that a term? I'm seeing like maybe. Not, you
Not
wouldn't bet on it,
really.
or
Yeah.
It was in heat transfer.
yeah. So
Yeah, it's the definition of convection. It's advection-diffusion.
Huh.
Oh,
I don't remember that.
yeah, then
yeah, I guess maybe it is the what you would call the combined effect, right? That's a reasonable thing. So anyway, I'm trying to stick with sort of simple models that have well-established names in the literature. Okay, so what we are going to do is consider some quantity that has things driving it, advection and diffusion. Okay, so advection should make you think of flowing material. I'm going to try to center this on nuclear-oriented applications. So rather than think of this purely as like a fluid flow problem, maybe we think of it as a molten salt system, right, used or proposed for a Gen 4 type of reactor, right, where you have fuel and molten salt all mixed together as some blob of fuel flowing through a reactor core, right? So that might be one place where we see advection. Then when we talk about an energy variable, this isn't necessarily, well, in the simplest case, it is actually just the energy. It's the energy of a single item, right? If it's a neutron, it's got a certain energy, it's kinetic energy. If we're talking about a molecule of water, it too has a certain energy. And so what we talk about today really applies both to neutron populations and, say, water fluids. Right? If we spend time, we could define terms applicable to either of those things. Okay, so when we talk about energy here, that's going to be primarily with respect to energy spectra, right? The distribution of energies of some population in some space. Okay, so what we do with all of this is we're going to start with conservation over a control volume, similar to what you might have done all the way back in thermodynamics. And then we're going to make some assumptions about the fluxes, or what we will call net flows. We're going to use some closure assumptions. By closure, that means that we will get rid of a variable from play. Okay, that's sort of a fancy word for eliminating a variable. Then we'll apply things like separation variables, and we'll get eigenvalues and the various modes that go along with that. And then once we get to that point, things reduce pretty naturally to different sorts of ODEs and BVPs that we care about. So my main goal, at least in the first part of this lesson, is to motivate where the hell these equations come from in the first place, right? The things that we need to be able to solve. It really helps to kind of go back and lay down a picture that you might be able to use to better understand why you learn certain things in Math 340, for instance, to solve things. Where do those specific equations come from? So, am I actually, am I sharing? I'm not even sharing. There we go. Share. Okay. So the first thing that we're going to do is assume that we have some quantity U. This is going to be a density. Now, density can mean different things. It can mean something like a number of objects in a unit volume, right? So my favorite example would be neutron. If we want to model neutrons, we can carve out some volume of space and say, hey, I expect there to be a million neutrons in this 1 cubic centimeter of volume, right? But it could be something else. It could be the mass of water in some control volume, right? Because at the end of the day, what produces that mass of water? A certain number of water molecules, right, in that fluid. So it could be any of those things. Then we will also assume that the species in question has some energy. So this is a little harder to imagine for water molecules, but you can say water molecules have a kinetic energy. It's maybe a little easier to imagine a free neutron in space having its own kinetic energy, and that's what we will be doing here, is assume that the population in this volume can also be broken down into its distribution of velocities or speeds, or equivalently energies E. So what we want is to quantify this density at some point in space as a function of its energy at some point in time, right? So it's all about the bookkeeping. Ultimately, what this quantity gives us is a an absolute number that we can use. So if we take that density, U at the point R, energy E, and time T, and multiply it by a small differential volume and a small differential energy, what that tells us is the expected quantity of the species. So that might be the expected number of neutrons per centimeter cube per EV, if we use EV as our energy unit, at some location, at some time. Okay. If we were talking about water, I'm not sure how we would qualify the energy of the water. We'd have to talk about it as being the independent water molecules, but it still is a function of energy. Now, this is where we start making, let's say, assumptions of the existence of quantities. What I mean by that is the following. If I have this density U, okay, and I want to integrate it over a volume V, any volume, I don't care what the volume is, right? I can do that. And then when I integrate that quantity over a volume and take its time derivative, that change in time must be driven by something, okay? So just a simple statement of balance follows. I can surround that volume with a surface area, and then I can count the flow of the species through that surface area, right? That vector J here is what in some physical context is called the flux. That's what I had earlier. We will recognize that from neutron diffusion theory as the neutron current. Right? But the key thing is to know that it is net flow. So that is telling us the net flow per area, per EV, per second. And at some point along the surface, you dot that with N to get the net flow through that particular surface element. And that represents your losses from whatever this is, simply leaving the control volume, okay? Could it be a source term? Could it be a loss term? It depends on what the net flow is, right? You could have net flow into a system or into this control volume or net flow out. It doesn't matter. It's listed here as a negative because we explicitly assume that it is a loss term, right? The net flow out of the system, where this N is the outward normal associated with the surface element. Okay. Now you've all had Calc 3, so like you've seen this sort of the use of vectors for volume integrals and things like that. So I don't have to go into all the mathematical nitty-gritty on these. I don't think. Okay. So these two terms, easy peasy. Okay. This term, where I integrate over S, is also pretty straightforward. That's just me inserting more of this substance into the system by some external means, right? So maybe this is a hose of water into a control volume. I don't know why we would have a hose going into a control, but we might. Or maybe it's a source of neutrons in a neutronic system. Okay? The complicated one is the middle term on the right. And that looks deceptively simple. I've used kind of a fancy script for the R. And what this is a reaction rate or interaction rate as a function of the density, right, of the position and the energy and the time, okay? So as written here, if I've got this balance for U and I've got this R thing depending on U, this could very easily become a wildly nonlinear problem, right? There's nothing, I haven't said anything about linear whatever. This reaction term, because it depends on the density itself, could be some nasty business. We're going, yes.
In this, at least in the 1/centimeter squared EV second and the 1/centimeter cubed EV per second, it looks like it's got density in terms of like that those variables are a function of density. Where'd mass go?
We don't deal with mass directly, because if you have a density and you multiply that density by or integrate the density over volume, that could be your mass, right? So if suppose you were actually the density of water, right? The mass density, right? This could be a mass density, right? I think it's easier to start off thinking of it as a number density, number of neutrons per centimeter cubed. But if each neutron has a mass, you multiply that number density by mass, you now have a mass density, just like you do for fluid balance. Yeah. So it's this the R term that is probably the most complicated of the terms, or at least could hide the most complicated part of this. That's where the physics of the system will live, and we'll see where that shows up. Okay. But this statement given in 1.1, it's nothing more than just saying, hey, you're accumulating this stuff in this control volume at a certain rate that is driven by either inflow or outflow from the boundaries, the local production or destruction from whatever these interactions might be, and then an external source, right? So balance, and it applies to just about anything that we could be putting into this control volume. Okay. Now, how do we deal with that outflow or inflow? Okay. So again, this is using the term flux here to mean a directionally flowing quantity, a net flow quantity. So keep in mind, flux as written here is like current in neutron diffusion, but flux as written here is totally consistent with things like the heat flux in conduction of thermal energy. Anywhere else you've heard the term flux when it relates to sort of a vector quantity like this?
Neutron flux?
So neutron current, all right? The heat flux is a flux in this domain. What about an electric flux? Right, you've got electric potential, then you have an electric flux from E and M. I don't know how much you would have dealt with that in physics too, but I assume a little bit.
Long time ago.
Yeah, long time. But just know it's a vector field. Here, we're making our first modeling assumption, or we're making our first assumption about which physics we might care about. Okay? So we're going to assume that that inflow and the outflow is actually a sum of two components. One for the advection of the material, which makes sense because if I have a material like neutrons, but they happen to be in a fluid, right? Suppose I have my molten salt reactor. If I've got neutrons in the molten salt, but the molten salt is flowing, well, now suddenly I have neutrons that are moving, not just because the neutrons are moving, but because the media in which they live is moving. Okay, that's the advection term. The diffusion term is based on sort of a simple observation. If I have a high concentration of something here, I will tend to have a flow of concentration away from that point, right? If I have a heap of neutrons over here, it's natural that those neutrons will start to flow away. They'll go downhill, right? They will go downhill until the hill has gone down and everything is equal, right? Everybody wants to get to equilibrium. Right. So the advective transport is pretty easy to define. That just takes our scalar density. And remember that U, it could be a neutron density, a number of neutrons per centimeter cubed, or it could be the grams of water per cc. Right? I take that density and I multiply it by a vector. In this case, that vector is W. That is the flow velocity of whatever the medium is. This did not show up in neutron diffusion when we had Ne630 because we assumed that our media, the background material in which our neutrons were propagating, was stationary. That's totally true for something like our nuclear reactor, right? Any geometric changes, any physical changes are going to be treated as like stepwise different scenarios, right? It will model the reactor with a control rod in or with it out. We don't necessarily model it as a function of time while that's moving. I guess we can do it, but that's a hard thing to do. Yeah. But the neutrons are not moving with those materials when we do model those other circumstances. Okay. So that's pretty easy. Whatever crosses a unit area in a unit time is just the velocity times whatever that local density is. Now, diffusive transport will take our substance and let it flow away from points of high concentration. That is embodied by something called Fick's law, right? So if you look at this, what this is saying is, hey, I've got some density U. And then I take its spatial derivative, right? So this is the gradient of U. This turns my scalar function of x, y, z into a three-component vector that tells me the spatial rate of change in each of the three directions. Okay, I multiply that further by this matrix, or what's formally called a tensor, right? But it's just if U has this scalar, its gradient has three components. D is effectively a 3x3 matrix, or it could be a 3x3, full 3x3 matrix. Often we will have that D, that diffusion tensor, is just a scalar quantity D times the identity. This means that the process of diffusion happens isotropically, meaning it doesn't matter which axis we're going, if we're neutrons, they're going to diffuse the same way, any way we look at it. Not always the case. There are processes that are driven by diffusion, but might have different diffusion properties in one direction versus others. A good example would be if you have alternating, let's say alternating layers of a given material, possibly for, I don't know, some sort of neutron detector, like some fancy system that has fancy layers of different materials. Maybe some of them are neutron sensitive, some of them are not. Neutrons that flow through perpendicular to those materials are going to have different diffusion properties than neutrons that are flowing within one of those layers, right? Parallel to the material. So there are definitely situations where you can construct a physical model where the diffusion, the natural propagation due to concentration gradients is not isotropic, right? Where it changes depending on which direction you take. But in the simplest case, we'll just take minus scalar d times grad u gives us that net flow of neutrons or whatever our species. Yeah. Again, this is all still implicitly a function of energy, right? Because maybe it turns out that fast neutrons diffuse differently from slow neutrons, right? Neutrons with lower kinetic energy. All right, now for that reaction term. We're going to keep it simple by keeping the model linear. And so what we'll do is we're going to take this local reaction term, which is a function of u and then the other things as well. We're going to write it as a constant times u, or at least something sigma that it's not dependent on you, right? If sigma depended on you, we would have a nonlinear problem, right? Because then we would have some function of u times u itself. But as long as sigma here does not depend on u, then we have no problem. It's a linear problem. This coefficient sigma here, you might recognize the symbol. I used it specifically because that's what we use for a macroscopic cross-section in diffusion, neutron diffusion. Okay? But it doesn't have to be a macroscopic cross-section. It can be some other coefficient that says how the density, local density is modified through interactions. Okay? So if sigma is greater than 0 here, this will be a sink, right? That means that whatever the species u is, we are going to be losing through some interaction. What might be a process that would cause our neutron density to be removed or lowered, reduced at some point in space? What could neutrons do that remove them from the system? They could be absorbed, right? So sigma in this case could represent an absorption cross-section. Okay. What other things could represent an absorption?
Oh, absorption, sorry.
Or removal of, like, what sort of interaction might remove this, whatever the thing that we have, this density of something, what other physical mechanisms might remove it from a system? So that's still, that's like an absorption reaction, right? So like if the neutron is absorbed by a nucleus, yeah, it's gone. What if we were talking about some other species?
But like phase change.
There could be phase changes, right? So you get different things happening if you have chemical reactions.
Poison, poisons,
Poisons and
poisons, poisoning.
well, so those things would show up as being absorption, right? That would all be built into an absorption cross section. So for neutrons, because we've had NE630, it's pretty easy to imagine scenarios where we would have a signature. But if we're talking about like chemical engineering applications where we have different, like two different chemicals mixing, then the amount of one species, if we put in two species and we're trying to produce some product species, then the amount of one of the other species is going to depend on certain reactions happening with maybe like an accelerant or something like that, right? So the math looks the same, but the physics, the application is different, right? But that's the great thing about these models is as long as you have a basic mathematical model, my recommendation is you pick your favorite application. You pick the one that gives you the language that you need to remember what the terms are. For me, that's neutrons, right? But as I've gotten older in life and spent more time working with engineers of different backgrounds, of course, I've learned some other physics that can also be inserted into these models, right? So it helps you be conversant with others, if you have to get technical about this sort of stuff. All right, so that reaction term, we'll keep it simple, but this is where a lot of the cool physics could be incorporated, right? This is where we could have neutrons from one energy being scattered to other neutrons, in which case we wouldn't just have pure absorption. We could also have the fission term here, where neutrons being absorbed could produce new fissions, right? That would turn this thing into something that looks more like a source term, right? A self-driven source term. We could also have an interaction that looks like U times something, right? What would that represent? Well, that would represent the density of the things interacting with itself. Ooh, that would be nonlinear, wouldn't it? Where would we have a situation where U might depend on itself? And what I mean by that, let me cancel. That's not what I want. What I want here, where's my annotate? Okay, if I have this, what if I had an R of U that looked more like minus sigma times U squared? What on earth would that be modeling? Why might we have something like that where we have a U squared? Self-shielding. There's probably a phenomenon that we call self-shielding. Remember, so first things first, if you see a term like this in a model, remember we're using generic language. Put your favorite physics into the picture. What is U if we're talking about neutrons?
Density.
It would be the neutron density. The neutron density is a function of space and energy. Okay. Where on Earth would I see a neutron density times a neutron density? It's a different tier. Okay, let's back up a moment. What's written the original model, sigma times. What would that? Where would we get that from? Regular old neutron diffusion. If you were the neutron density, and you might remember the neutron flux is the density times the velocity. Right? So in this case, we could actually substitute U for p. Right, the only thing we'd be missing is that velocity factor. So let's forget about velocity for a moment and just insert phi. Phi times sigma gives us a reaction. The flux times the neutron flux times the macroscopic cross section gives us a reaction. Same thing, like a photon flux times the linear attenuation coefficient gives us a reaction. Remember that from 495? Yeah. Do you remember what the units of attenuation coefficient are? Usually it's per centimeter. I mean, you can have mass attenuation coefficients, but it's like you've got a field multiplied by this coefficient, and you get the number of things happening per second. Okay, that would normally be broken down like our flux times macroscopic cross section, but macroscopic cross section is actually equal to the product of two things: the number density of the surrounding medium times the microscopic cross section. The same thing is true for shielding applications. Okay, so the sigma here would be a number density times a microscopic cross section. Well, what if that number density were not for the background material, but were for the neutrons themselves? If you have a density of neutrons, number density of neutrons, and if each neutron had a cross section that another neutron would see, couldn't you have something that looks like a sigma times U squared? So some constant times U squared, you can't. And in fact, in general, that term exists if we want it to be fully legit when modeling neutron transport. But what would that require for that to be a meaningful term? That the number density of neutrons, in this case the U, is sufficiently large that self-interaction terms like neutron-neutron interactions would be meaningful. In many cases, that's simply not true in a relative sense. The number density of this table is something like 10 to the 22 atoms per centimeters cubed, right? Even in the largest neutron fluxes that we see in reactors, we're way, way below that. Maybe like fluxes of 10 to the 15, 16 at peak. Yeah.
So in this case, in the equation that you typed up there, sigma is the microscopic cost.
It would have to be something like
you just took the look up the macroscopic and you split it up into its
Correct, yeah,
So
yeah.
it should be
It's-
uppercase.
It should be, I just view that as a constant of proportionality.
Okay.
Yeah.
I think
Yeah,
that's where I was-
good catch.
I think that's where I was confused because you used uppercase S, so I thought.
Yeah,
it was
yeah, yeah.
It's still a bigger sigma.
Yeah, if I were really doing this, this would have to be like a sigma, and I would write it as a neutron type thing. Yeah. But we'll keep it like this. Just know that there's a lot of physics that would go into this term if we wanted to include other applications, right? And that's what we don't have to focus so much on that. Let me get rid of this. All right. Okay, so now I do a very quick jump over some math, right? If we substitute the expression for that reaction, we put in the two flux terms or net flow terms from diffusion and advection, we get this equation 1.5, okay? Now is where your Calc 3 information becomes useful because we can simplify this equation 1.5 into this equation. Now, why do we want to do that? What's the problem with 1.5? We've integrated, we've got integrals, but those integrals aren't over the same domains. We've got an integral over volume here and here, but this one is over that surface where we're counting up all the losses or gains from flow. So we take that integral over the volume surface and turn it into an integral over the volume using this thing, the divergence. Right? Do you remember that by name? Yes. Does it ring a distant bell? The divergence theorem? Just know that if you are adding up if you have a contained volume and you're counting up the stuff that leaves the volume, you can turn that into a problem of counting up something within the volume. Right? That's the key thing. Why do we care about this? What happens when we take 1.5 and we make the substitution we get from the divergence theorem? We get this, which is this, turning into this. So we take this, move it there. Now we have an equation that is in terms of only integrals, and those integrals are all over the volume. What's nice about that? What can we do then?
Add them.
Well, we could, but once we have an integral on both sides over the same volume,
You just get rid of the.
now we get rid of the integral over the volume, and what we're left with is a balance over a differential volume. When you have a balance over a differential volume, most likely you have a certain kind of equation, a differential equation, right? So we start up, we add things that go into this little box. We make sure we do all the bookkeeping we need to do. And then if we've done that right, we end up with our constitutive differential equation model, our mathematical model for the system that we care about. Okay, so when you do all that, we get to this equation 1.6, which is the 3D advection reaction diffusion equation. Now, as written here, totally complete in a sense, right? Because this accounts for all of our spatial derivatives, our time derivatives, and specifically, it doesn't actually say anything about the coordinate system. Right? I motivated it with X, Y, Z because that's the easiest way for me to think. But when you use the vector notation, this is still completely okay for any coordinate system as long as you do what? You substitute the right coordinate system definition for the divergence, for instance, and the gradient. Yeah, right. So for a gradient for Cartesian, it's just d dx, d dy, d dz along I, j, and k, and then same thing would be applied here. So easy peasy. All right. So each of those terms is listed here. If we further expand this into those Cartesian coordinates, right? Just doing the product rule, you get something that's actually kind of long-winded. But if we make some assumptions, one good one is, let's take the divergence of W, the flow field, to be 0. What does this mean?
Incompressible flow.
It's incompressible. What does incompressible mean?
Static volume.
Static volume, yeah. The volume does not change, or the mass in a volume is conserved, right? Both of those things are true, right? The density within a volume is unchanged. Okay, so you do that, and of course, incompressible flow is an important flow regime, like water, for a very good approximation. We view it as incompressible. Maybe not so much when you get two-phase, but that's a different ballgame. Okay, but once you make these assumptions, we end up with this nice compact form for 3D advection diffusion with reactions. But that's not the whole story, because that just gives us kind of an ugly looking partial differential equation, right? Why is it partial? Well, it's a partial differential equation because I have a partial derivative. Why do I have a partial derivative? Well, because I have a balance that incorporates more than just one independent variable. I've got my time and then the upside down triangle symbol, so gradient or the Laplacian here is your spatial derivative. So you've got spatial derivatives and the time derivative all in one. In order to solve such an equation or make it complete, we've got to have some initial or boundary conditions, right? We could solve this and we would have a sort of a bunch of undetermined coefficients from integration. So if we want to nail down a full solution, we've got to set some boundary conditions. One thing we can do is to set an initial condition where at time 0, we know what the density is. We know what U looks like. Okay. But then when we start setting things on the boundaries, right, spatially, we can prescribe what that density is, right? This would be called a Dirichlet condition. This would be me setting what my neutron population is at a given point along the boundary. Or another great thing that we can think of in place of U is temperature. Right? Temperature would also be something that we could place. Is temperature really a density? Not really, but it's something that we could put into these same equations. We could also define a Neumann condition, right? So this is saying something about the inflow or the outflow from a boundary, right? So if we've got the grad U times D, remember that was my flux, and then multiply that by n, right? Dotted with n, the upward normal. We could state that that is a given value, or we could mix it. We could have both inflow and outflow specified along with a fixed value, right? All three of these boundary conditions have practical purposes when modeling systems. Okay. One thing is when we do have second order derivatives, right? These are second spatial derivatives. That's like d squared dx squared. Okay. That will almost always require that we define boundary conditions around the whole boundary. If instead we don't have the second order, if the diffusion term goes away and we're driven by advection, then we'll typically only have a boundary condition for inflow, right? We're not going to specify what comes out of the system because we have to solve the system first. All right. So to simplify the equations we have so far, we've got to do something. And I put this in here and it almost felt contrived, but I think it's good to show what you can do to get rid of a variable, independent variable right away. And so the first thing we're going to do is get rid of energy. So we've got this density U that's a function of R and energy and T. But what we're going to do is assume that it's separable, meaning that we can write U always as a function of R and T alone times some function that is a function of E alone. The A here is for amplitude, right? So this is the energy amplitude function, or what we would call the energy spectrum, right? And so that has to be greater than or equal to 0. And when we integrate it over the entire range of energies that we care about, maybe that's 0 to infinity, that has to be 1. So when I have a function that is greater than or equal to 0, and its integral is 1, what have I defined? What sort of function is strictly non-negative and has an integral of 1?
PDF.
A probability density function, right? So when I say neutron energy spectrum, or energy spectrum in this case, and when I make these constraints on it, I am defining its amplitude function as a probability density function for the distribution of, say, neutron energy. Okay. So now we've got that energy amplitude function, and now we've got the spatial and time amplitude function. Why does that matter? Well, if we substitute that normalization into the equation that we had, then we end up with this equation, okay, where we've broken up the unknown into both an A term and a B term. Okay, but what can we do now? Integrate over all energies. And when you do that, you end up with a very compact equation given here 113 box with these coefficients that are averages over that energy spectrum. Right? Should seem very familiar to any 630 students, but the idea is that we have produced an average value. We average all these coefficients over what we assume to be that energy spectrum, and we end up now with a partial differential equation that is in terms only of time and space. Okay, that's useful because that's what we can start to solve. All right, what do we do now? Anybody know how to solve an equation like 113? Laplace transform? That'll get rid of your time dependence. You'd still be differential in space, and then maybe you could solve it there, right? So what could we do? Well, there is a technique known as the separation of variables, right? So let's assume that we can rewrite that problem in the following way. Let's take that time derivative of v and let that equal to this fancy script L times v. What is that fancy script L? Well, I use the fancy script just like I did before for R to indicate that it is like almost like a matrix, and that it is this thing that multiplies this other thing. Okay, but because it's multiplying the scalar, it's not really a matrix, but it's also not a constant value. It's not a single function. It's an operator. It operates on V. So that fancy script L is an operator. And what does that operator do? Well, it does the second spatial derivative, right? This divergence term, and obviously it includes everything. So in this case, it's actually a differential operator. In this case, it's also a linear operator because we see V only as functions of V, not V squared or anything like that, but we see derivatives of V. So it's a linear operator, but it's a linear differential operator. Okay. And then if we have our incompressible flow, this term simplifies a little bit. Okay. Now what we do is we seek a solution where we can take the spatial component and the time component and treat them again as independent. Okay. This seems similar to what we just did with the energy. Right. The difference now is we are going to retain the coupled spatial and time dependence, as opposed to getting rid completely of the energy dependence. Before we took that energy variable and we just integrated it away. Now we are going to retain space and time and treat them explicitly as we go along. So if we make this assumption, right, what we could call an ansatz, right, an educated guess, we put that into equation 114, right, our original PDE, and we end up with this relationship. Okay. Now, as long as R times T is not equal to 0, we divide through, and we end up with this equation here in terms of alpha. Okay, this is what we call the separation constant. Now, if we take that alpha and then treat that as constant, what that really means is we have two separate differential equations. One is first order for T, the time magnitude, and then one is this thing for the spatial. Now notice this still includes the fancy L. So, I'm getting close to done. How much time do I have left? 10. Yeah, we'll wrap up. Okay, so this one is easy because that's just a first order differential equation with a constant coefficient. By definition, this alpha is assumed to be constant. That one we should all be able to solve in our sleep, because it's just a derivative is equal to a constant times the function itself. What function is proportional to its derivative? Exponential, right? So that exponential happens to be e to the alpha t. So that one's an easy one. Solving this one's going to take a little bit more work, right? Because L is a little bit more complicated. Yeah, we don't know exactly what alpha is yet. It could be negative, it could be positive. In fact, it could be complex, right? In which case, that exponential has an I in it, and then we end up with sinusoidal, right? As opposed to exponential decay. All right. Now, the equation here, LR equal alpha R, let's assume that that has a solution, and that solution can be cast in terms of these functions R sub n. Okay. What will happen is this ends up being an eigenproblem, and then these will be eigenmodes. You remember eigenvalue matrices and eigenvectors? It's the same concept, right? Where we can split this into a number of modes, each with a corresponding value of alpha, because it will turn out that there's not just one value of alpha. There's actually going to be possibly an infinite number of alpha terms. Okay. So what do I want to do here? I'm going to skip this stuff. That takes us a little bit beyond what we want to do. And in fact, I think I'll skip to the next thing here, right? I'll upload these. I'll do a little bit of editing and then get it. But I did start this. Okay. There are a lot of simplifications we can make to the equation that we saw earlier, right? If we get rid of all the space, we've already gotten rid of energy, right? We integrated over that. But if we got rid of space and we have no time, well, the only thing that pops out is sigma u equal S0. Okay? Why is that useful? Well, that's not a differential equation at all, right? If you get rid of your spatial derivative, right, by assuming no spatial variation, and you assume your steady state in time, meaning no d dt, the only things that are left are what are written there. That's algebraic, right? If we assume time dependent but no spatial variation, we end up with u prime is equal to the reaction term plus S naught. Well, that's a first order IVP. That would mean that it's well mixed in the sense that nothing is happening in space, right? Everything that's happening in time is happening everywhere in space at the same time, right? No changes in space. That looks like a problem that we've seen before, or that you should have seen before in something like NE495. Imagine that U gets substituted with an N. Imagine that sigma gets replaced by a lambda. And then suppose that S naught is, well, I don't know what you call that. Call that an R or a P or something. That's radioactive decay with a production term, right? If we do steady in 1D with no diffusion, then we end up with this differential equation, right? So that's our speed W. That's our gradient, our time derivative of U. Spatial derivative of U, the reaction term, and then the right-hand side. So that's first order with inflow data. Right? That's an advection reaction equation in 1D. If we have a steady state 1D, no advection, but we do have diffusion, we have a minus D U double prime plus sigma U equal S naught. Does anybody recognize that equation? Substitute D for U. Maybe a sigma A for sigma. But otherwise, isn't that just the 1D diffusion equation in slab geometry? Yeah, it's all this stuff comes from the same. You have not had any 630 yet, right? So you like this, it'll sink in when we get there, right? I'm being a little, I'm leveraging the fact that some of you have seen that before in this.
Do you think next year this process could be a little bit different since a lot of your students next year have not taken that?
Yeah. But in a course like this, that's starting from, not scratch, but when there's a definitely shifted mission,
Yeah.
you gotta throw something out there and go with it.
Yeah.
That's all I can do. Right? But yeah, there's a lot of finesse that can go into this stuff later on. Okay, and then if we have time dependent without spatial variation, but maybe we have two species, we'll call that Y. So now we have a density of a U and maybe a density of a U1 and a U2 that we pack up in Y. And then we have some sort of coefficient matrix along with that forcing function on the right-hand side. That would be like a linear system of IVPs to model, point kinetics, right? Like the neutrons and precursors in a reactor system. So from that very first PDE, a few assumptions further give you the equations that you will see for the rest, like throughout your nuclear engineering curriculum, right? If you haven't seen it, you'll see it, but everything falls under this sort of structure, Okay. The only thing that doesn't is full-on neutron transport, where we have to incorporate a little bit more than what we've done here. That's direction, things like that. For the balances that we care about, this structure gives us everything that we need. Okay. So we've got what, about 20 minutes left, and I've got how many minutes left on my battery? 10 minutes. Oof. I am thinking for our purposes that we break for the day. I am happy, so you all have project 3 that you are starting. So let's do the following. For the rest of the time, I will answer questions about project 3. So I will stay online as long as my computer stays online. I'll get these notes uploaded for you to read. And then on Tuesday, we will pick up and start solving some differential equations. And we'll start off with first order systems and Euler's method and things like that, and kind of build on from there. And we'll end up with we'll stay in 1D, I think. Except for a previous project that have a 2D variant to connect to the project that you do now. But, so, any questions about project 3?